All right. Welcome everyone. I guess we're live. Welcome to lecture 42 of GPU mode. Like today, I'm really thrilled to have like the legendary Adam Paszke, who's here going to give us a talk about like Mosaic GPU. For context, like Adam, thank you. Like I work on PyTorch, so like partly thanks to you that I have a job. So thank you. What's also cool is like Adam also I think worked on many languages. Like if I'm not mistaken, like I think like you worked on PyTorch, JAX, DEX, and now Mosaic GPU. So I think if you're like a PL nerd and want to see sort of how these things evolve, that's why I'm personally very excited about this talk. So yeah, Adam, glad to have you here, and please take it from here.
Yeah, thanks a lot for the great introduction. I don't think this sadly will like go through the history of all of those languages. I will start with a bit of context for why I am working on those particular languages right now. But yeah, we can try to do the history another time. This time it will be primarily focused on what we're actually doing right now. I also changed the topic of this talk slightly, actually. It was meant to be primarily about Mosaic GPU, which is sort of the project the particular project that focuses on GPU programming. I actually decided to widen it a little bit, and so there will not be that much Mosaic GPU code directly. And this is kind of a decision that we've made some time ago. Basically, we actually do want to push people more towards Pallas. This is another language that we're building, and we've been investing quite a bit into sort of the bridge between Pallas and Mosaic GPU. Just because we think it's like much better user experience, and we can essentially, it's much easier for us to develop nice features, and it's much easier for you to actually use them. Anyway, the whole motivation for why we'll be looking at this is we just want to have a DSL for fast Hopper and, well, at this point also Blackwell kernels, and we also want to program them from Python. We do, Triton was extremely successful, I think partly just because it was like so easy to integrate. And I think that was a great decision. And so we also want to kind of follow the same principles. I should also say that, I also, started kind of this project, the Mosaic GPU one, but at this point, there's also a lot of other people who have, joined along. And so I also can take like full credits. People from JAX, from Google and NVIDIA as well have contributed at this point. We're very happy about this. Everything actually I will be talking about, both Pallas and Mosaic GPU are actually fully open source. They're part of the JAX repository, so you can find all of the code. Contributions welcome. We're happy to talk a little bit about this kind of closer to the end of this talk. Anyway, so why are we even talking about this at all? So the motivation for me here is I think there's been a little bit of a change in the role of like ML libraries and languages that we're designing. Essentially, back in the days when we were starting out with PyTorch, I think one of the primary really goals that we had was to increase the sort of generality and usability of ML or just numerical programming. Of course, subject to acceptable performance, right? Scaling always mattered. If you were to like use the accelerator really badly, it would still be unacceptable. But it was okay to take like a, I don't know, 20-30% performance hit. No one would complain for as long as they could, just like get their research done faster, right? Developer velocity ultimately matters quite a lot as well. Now, these days, the problem is that, transformers are like unreasonably successful. And so most of the models that we do these days are actually transformers. And so sort of the generality part is no longer plays that big of a role. Transformers are also relatively simple models. It's just like, matmos and a few ops, intermingled. They're also, I think, maybe partly successful and actually also really well co-designed, I think, with the accelerators that we have. So, modern GPUs, TPUs, for example. And so we're much less focused on just like enabling any weird computations to happen. We are actually more interested in making the one big and extremely useful class of computations we're interested in to happen, to make people productive as they're trying to sort of squeeze out performance, right? We do understand very well that scaling matters, and whether we're talking about scaling up where saving any percent is potentially saving a huge amounts of money, or if it's scaling down where, those models can be big and you might want to like serve them on like a smaller configuration, you still want to use it reasonably well so that you actually don't have to use too many devices to do this. Of course, all of this happens actually subject to usability. You could just implement everything in assembly, but of course that will be a pretty miserable experience. There's still modeling changes that happen day to day, and so we still want to like maintain some developer velocity. But performance engineering kind of comes first and foremost in all of those approaches. Reaching peak performance really will be the goal, and then we want to make reaching peak performance sort of nice for as nice as is possible, essentially. And so also why kernel DSLs in Python? So there are a few reasons. I don't think I have to convince anyone that prepackaged libraries are great, because if they satisfy your use case, they generally achieve really high performance. But oftentimes you do want to change it slightly, and then it's a problem. You fall off a very steep performance cliff. Then another solution you could follow are compilers. The problem with compilers that sort of do really sophisticated optimizations is that they actually take quite a lot of time to take quite a lot of time to adapt and develop. For example, as new architectures come out, if you look at the evolution of hardware from Ampere to Hopper to Blackwell now, the programming of those different generations is actually quite different. And so if you want to make a compiler that supports a large number of use cases, it takes quite a bit of time to make it fully complete. Then there are approaches. There is a number of libraries you could use to implement kernels in C++. I think that's fine. Me personally, I think the biggest issue for me with this is that as I implement kernels, metaprogramming ends up being really useful, I think. Essentially, usually there are multiple different evaluation strategies you could try, or maybe you want to make it easy for people to integrate a little, I don't know, element-wise fusion or something into the kernel. And C++ templates are just don't feel like the right tool for this. These sort of error messages are kind of gross sometimes from the compilers, and you don't know what's really happening. It's not really C++ has a monopoly on generating fast code. Ultimately, it does not matter what the input language is. What really matters is how do you end up generating the code. And Python can be a perfectly fine front end for generating code that reaches peak performance. And in my opinion, this metaprogramming path, for example, is significantly simpler in Python. And so ultimately, in my opinion,
I know you prefaced this by a personal opinion, but I've seen sort of different takes on this problem. For example, yesterday we had a speaker from Flash and Fur who was sort of doing metaprogramming by writing strings. Basically Python, writing C++ strings from Python. I think Inductor follows a similar approach. Cutlass goes more all in on C++ metaprogramming, and then I've seen other projects like Trident and yours sort of go more into MLIR. Could you sort of I guess for the rest of us kind of explain what you view as sort of the trade-offs and how you reached your preferred choice in this design space?
Okay, so at least talking about the three cases, Trident is also quite different than what we'll be doing. I do not have slides on this, but I can say a few words about this. So maybe let's actually talk about the four approaches, right? First of all, you have C++, which basically, historically didn't have that much support for compile time. Metaprogramming, really what we're after is compile time evaluation, right? And in C++, they are building out language extensions with const.expr and stuff like this. That sort of makes it easier, but it's still relatively brittle, I think. And sort of the most powerful thing you can do is probably still templates. The problem with templates, as I find, is you can generally encode anything you like in them. It's just that, as I said, the usability of programming with templates, or especially debugging if something goes wrong, is pretty bad. The C++ compilers just have not invested a lot of time. Well, or maybe they did, but it's just a fundamentally hard problem to provide great error messages for a sort of weirdly encoded program that you just end up evaluating through template expansion, right? Haven't spent too much time thinking about it. Either way, the error messages are not great, and this is fundamentally the problem. So then stringly typed metaprogramming, I guess. Sure, that works. It's just that, we usually, it can be successful if you're doing relatively small modifications of the program, you're going to paste a subprogram in there. There's a bunch of issues though, right? You have to sort of be careful to manage scoping, names. You have to make sure that if the string you're pasting binds more variables, then they will not shadow the variables that are in there. There's it's generally not the most recommended way, I think, of metaprogramming. And because of issues like this with lifetimes of bindings and so on, it just can be like kind of hard to have like a sane way of actually doing this. So then at the end, there are those two approaches in Python. One is you just parse the AST. And this is kind of like, I think this is similar to C++ ultimately. This is what Triton does, with the only exception of you, get to implement any kind of compile time evaluation you find useful. So Triton has those like constexpr, constructs, and they get to evolve them without, involving a whole committee of like C++, evolution, right? And it doesn't take years. They can just like change it if they need to make it more powerful. You get to do it. So this is one upside. It has the upside of like, if you have Python control flow, then it gets staged out into the actual runtime program automatically. But metaprogramming, again, uses this sort of funny two-stage thing where like some expressions are constexpr, and there's not like that strong of a distinction, I think, between them. Finally, you have Pallas, and Pallas follows the same approach as JAX, which is generally tracing. So it sort of assumes that you're not doing like really weird things with Python, and it will just like evaluate your function once pretty much to just like try to construct a model of what it will be doing. The downside is that if you have native Python control flow there, it just gets essentially evaluated out. So if you have like an if, only one branch will be taken. If you have a for, it will essentially unroll the code, which can be a problem. You can still do control flow through like special combinator helper functions. But at the same time, in fact, this thing where like ifs and correspond to just specialization to one branch and fors correspond to unrolling is actually extremely useful for kernels. Like unrolling, there is like pragma unroll or whatever that you can tell NVCC to like unroll a C++ loop. But in Python, you could just write a for loop, and actually it's guaranteed that it will be unrolled just through tracing, just because of how like this program will be interpreted. And so actually this metaprogramming becomes really easy, because anytime you have Python control flow in your program, it sort of is the metaprogram that you will use to generate ultimately the code that will be running. Hopefully that is useful. Yeah.
That's word of course. Yeah, thank you, Adam. I'll let you keep going.
Okay, cool. We're still on the second slide, so we should go. Or the third one. Anyway, in my opinion, we just need like a great playground where we can do rapid development. I do want to like maintain the velocity, but I do really care about sort of implementing really good manual kernels. Like I ultimately do not want to sort of automate. I want to automate as much as possible, but ultimately we're not at the point where like the compilers can make perfect decisions for us. And so we still need like a big manual component, I think, if we just want to reach peak performance. And also, if you are to achieve this, you should also have an increased visibility of sort of very low level hardware details sometimes. Like you will want to take advantage of every sort of trick the hardware is able to do. And so you need to be able to access those details. We kind of will care less about portability, for example, right? And we will want to enable people to use every single trick. So just a few.
So sorry, Adam. Like, so one of our regulars, Eric S, couldn't comment on YouTube, so he wanted to relay a question, which is one thing that's interesting from the C++ versus Python discussion is the fact that certain libraries like Thunder Kittens use C++20, which seems like a very recent version compared to the typically long backward compatibilities in HPC software. I'm pretty sure that this is because of the new metaprogramming const expression stuff that gets introduced in C++20.
I would not be surprised. I know that recent versions of C++ are way better in that regard. But yeah, I don't know. I'm also not like a C++ expert, and it just seemed like a lot harder for me to get into this. And yeah, even if you have a like context before, I don't like this will not correspond to like code unrolling. I think like you can't. Again, not an expert, but I think if you have like a context before, then it has to like fold into like a value or something at compile time. I'm not sure if you can like actually unroll a loop through this. I don't know. Not an expert. I know that in Python it just works out, right? We do have languages that use this. We do have JAX, for example, and we know it generally works, and it's great for. And actually, while in JAX it can be even annoying that you can't stage out Python control flow easily, for kernels I actually consider this a benefit because again, metaprogramming is sort of everywhere. Maybe in modern C++ is actually not that big of a deal, but I personally have not used Thunder Kittens, so I also don't want to like. I think Thunder Kittens is a nice project. I think their blog post was great, So yeah, I don't want to say bad things about them. That's why I prefixed it with personal opinion. Maybe we should also move on because I don't want to turn this presentation to language war. Okay, I will not be firing more shots here. So, okay, a few words about how Mosaic GPU is designed currently. As I said, it's fully open source. It's integrated into JAX, and it's in JAX packages. There are also early PyTorch bindings, so you should also be able to use Mosaic GPU kernels from PyTorch without like any copies or anything like that. There are really two DSLs, as I said. Like one is sort of the original Mosaic GPU DSL, which leans very heavily on sort of MLAR Python builder APIs, which is also tracing based, exactly like sort of the JAX and Pallas APIs are. So at least sort of the flavor of the DSL is maintained. And then there's also just like a bunch of abstractions and helpers for programming GPUs that it provides. And then the second one is actually the one that we will be talking more about today, because I do want ultimately you to potentially use this one. And it's sort of the backend of Pallas to Mosaic GPU. I also, I specifically, use this column here because Pallas is not Mosaic GPU specific. Mosaic GPU is in fact a third backend to Pallas. Pallas initially started as a sort of more JAXy Triton front end. Then over time, we've built out the second backend, which was Mosaic TPU, because now Pallas kernels actually can be compiled both to GPU through Triton and to TPU through Mosaic TPU. Now, Mosaic GPU is sort of the third backend we're developing to essentially, explore some of the more low-level programming with GPUs. And so the language is still a little bit more low-level than the other two backends, but it's still like roughly in the same. The abstractions and the concepts roughly fall into the same category because ultimately the hardware is very similar. Roughly speaking, one Mosaic thread, as we're talking about GPUs, thread is a very sort of overloaded term. When I say thread in Mosaic, I will mean a single warp group from the CUDA definition. Ultimately, I don't think for like dense linear algebra applications, I don't really think it makes sense to sort of partition, like expose the GPU as like something more fine-grained than a warp group. I think going blockwise like Triton goes is like a little high already as an abstraction level, but I think anything below like a warp group is a little bit low. And so this is kind of where we landed. And yeah, as I said, all features of the hardware I think really should be exposed. You should be able to use any tricks that are allowed. And what we really care about is like, we ultimately want to take we want to make your programs LLM proof. We want you to not feel like you have to reach for an LLM to write a kernel. We want to like get rid of all of the boilerplate. Your sort of kernel should be like maximally information dense. Like all of the sort of performance parameters should be there, but there should not be like a ton of sort of setup code, etc. Right? Anything that is like essentially automation is welcome, but only when it's unambiguously good, right? Only when it's boilerplate, we want to take this away from you. But if there's like any sort of insight you might want to have that would have a big impact on performance, and it's not like a simple optimization problem that a compiler can just like run through, we do not want to automate this. We actually want to expose like a manual knob that will do this. And ultimately what you end up with is just a short program, which is like very sort of information dense. And yeah, also it's a relatively small project, and I think it should be hackable. I just run like a summary. At this point, it's like 6,000 lines, which is maybe not the tiniest project, but as we're growing more features, it's not surprising that it grew a bit. But it's still like of a size where a single person can like reasonably hold it in their hands if you like spend some time reading through it. A lot of it like with helpers for like arrays fragmented over CUDA lines. It's not that interesting. You don't have to like know all of it. So I think it can be like reasonable to work on if you want to play around. All right, so now let's actually start looking at Pallas. And this will be, initially I just want to tell you about sort of Pallas more in abstract, why we've designed it this way, and then we'll move on to Pallas Mosaic GPU specifically, and I'll show you how you can use some of the sort of new features of the modern GPUs, like async copies or warp group MMA, to essentially write some kernels. But yeah, first let's just start with abstract Pallas. So this is sort of the simplest program you can really write. So you can import Pallas from JAX Experimental. We usually import it as just PL. And in JAX, normally arrays are just like immutable, ND arrays, kind of like NumPy or Torch tensors, only you actually are not allowed to mutate them. In Pallas, this changes. Actually, all of the arguments to a Pallas kernels are references, but they are shaped. So in particular, you will find a lot of those like slices that really do nothing. If you just applied this slice to like a NumPy array, you would basically get the same array back, which seems kind of nonsensical. Only for Pallas references, what this means is actually read the value from xref at this particular moment, because they are mutable, right? And so the result of this expression will actually be an immutable array. And because it's in a kernel, immutable arrays generally, you can think of them as like values you store inside registers. But yeah, so in this case, we would load the value from xref. We would then load the value from yref. We would add them together again in registers, because at this point they're like loaded values. And then you store it to zref. Again, you can't just say zref equals this without the brackets, because that would just like replace the Python variable. But because you can kind of think of those brackets as like a dereferencing operator, like a star in C++ or C. That's how we use it. And now for compute inside this kernel, this maybe is not the best example because it's just like an overloaded plus in Python. But you get to use many of the JAX NumPy functions, essentially. Not every single function works, but you can basically program in here using regular JAX NumPy, which is also nice because you don't have to like learn another programming like set of operations on arrays, I guess, just to write a kernel, right? It's pretty much just NumPy. Okay, and then to actually call this from JAX, right? JAX does not give you those arrays normally. JAX only gives you, JAX doesn't give you those references normally. JAX only gives you arrays. So you need to somehow convert this add kernel into a function that actually can be called with regular JAX arrays. To do this, the most basic way is to use the Pallas call, sort of higher order function. So basically, you give it as the first argument your kernel function, and what it will return you is essentially the sort of function you can actually apply to JAX arrays and get JAX arrays back. So you can see you get this JAX add kernel, which you can call on some arrays now. Now, there are only slight differences. Like, for example, you actually do have to declare what will be the shape of your output, because that will be allocated by Pallas for you. And so you can see there are two arguments, the kernel on the outside. Inside, it gets 3 references because we append essentially these sort of place to write outputs at the end of the argument list. And so you can see here, we just say, oh yeah, the out shape is the same shape in D type as the first operand because it's just an add kernel. Now, this kernel is also not very interesting just because it would just evaluate this body once. There would be essentially one thread, whatever a thread means for a particular backend. Like on Triton, it would correspond to a single block. In Mosaic GPU, it would correspond to a single warp group. And to actually utilize the parallelism in something like a GPU, you still have to invoke a few instantiations of this kernel in parallel. If you've used CUDA and you probably know what's happening next, we just add a grid parameter, which will be a tuple of integers, which basically says, well, we want to have like a number of independent invocations of this program, as many as the product of the integers in that tuple. We also modify the program so that we sort of query which program we are. Since the grid is 1D, we just say, yeah, give me which program I am along the first axis. We construct a slice object. The DS is just like syntax figure for dynamic slice. Essentially, the shape here, it says start at PID times block size and take exactly block size elements. Now, and then we just apply the slice. We replace sort of this trivial slicing that we had before here. We replace it with the slice, and that makes every single thread, operate on only a subset of elements, right? Now, one thing to note here, as I said before, those references are shaped. They're not pointers. So you also do not slice them using, a range and sort of integer arithmetic. You just use sort of slices, regular Python slices. Integer slicing is allowed. So like most of the basic slices you would use again on NumPy arrays. Advanced indexing is not allowed generally right now. But like the sort of structured ND slicing, you can slice multiple dimensions at the same time. This is allowed. I just find this to be sort of a little bit easier to program ultimately. That this is one of the few things that the compiler actually can automate for you reasonably. Triton also added block pointers after some time. I think this is like the direction we should be going into, and so Pallas also follows the same pattern. And if you were just programming like classic GPUs, kind of not thinking about tensor cores too much, That would actually be pretty much it. We would just be done. We would not develop like any other changes, but we didn't stop there. Well, one of the reasons why we didn't stop there is, we're at Google. We actually do want to program other devices. Like, for example, we do have actually quite a few TPUs lying around. And for TPUs, you can't rely on the same sort of programming model that classic GPUs use, right? Essentially, this access here, those references, if they're in HBM, if they're in global memory, they have really high latency, right? And so classic GPUs kind of played this trick where they would have like a lot of work in flight, and they would just like, make it go to sleep and then wake it up once the memory comes back. But if you have enough work in flight, hopefully no one, like the device has always something to do, right? On TPUs, this doesn't work. They do not have this like fancy scheduling thing. You have to like plan your program much more carefully, sort of as you compile it. Interestingly, modern GPUs are becoming much more like this. Like once you're interested in using tensor cores, and especially the like big instructions, like warp group wide MMAs, you end up, your footprint of like shared memory or registers is so large that you also can't have like a few blocks allocated on the same SM, right, on a GPU. So you also don't get to use this. And this is partly why modern GPUs introduced TPU-like features, like, async copies, for example, right? And so this programming model, I think, while maybe nice and historically really relevant, this ultimately is not how modern accelerators are evolving, right? And I think it's really interesting.
So Adam, sorry to interrupt your train of thought, because we have a bunch of questions. The first one is, so Gregory Axler is asking, so like, will Pallas auto-schedule things inside a warp group? So maybe if you could briefly talk about like the scheduling.
Wait, so you're going to repeat the question?
Will Pallas auto-schedule things inside a warp group?
I'm not sure what auto-scheduling means. I mean, yeah, you are, again, it depends on the backend, right? So again, on Triton, a single thread or like a single invocation of this program, like a single, program ID corresponds to a block. In Mosaic GPU, it will generally also correspond to a block, and by default, the block is like size of a single warp group. You will later see ways to like get multiple warp groups in a single block, but a single thread will be a warp group even if they belong to the same block. And then sort of ultimately to program GPUs, you have to generate PTX and then SAS. And SAS and PTX are programming languages that sort of target the hardware at the level of a single CUDA lane, which is different. And yes, the mapping from, let's say, the warp group level or the block level to the sort of single CUDA lane level, this is done by the compiler. I hope this is what you mean by auto-scheduling, but yeah.
So the second question is, unfortunately, it sounds like it's a language wars question, but I'll ask it anyways. So this is not Pallas specific, but in the age of LLMs that are increasingly capable of generating code in well-known but perhaps less ideal languages, does the calculus around creating DSLs change?
Does what around DSLs, sorry?
Yeah, so basically this person is effectively asking, like, if we have if we can have an LLM just generate basically the low-level language, like, what's the point of having a DSL? So it's like sort of speculating around the future of LLMs being able to generate systems languages.
I mean, this is a bit of a... Okay, it's not a question I have a prepared answer for. At least one thing that immediately jumps to my mind, right, is that we write those kernels for really high-stakes applications. Like those kernels, if we train like a new LLM, they will be running on like thousands of devices for months. This is like a lot of compute time. If the kernel is bad, it's like a lot of wasted money, power, and just like opportunity. We could have done something useful with this hardware, right? So it's a relatively high-stake application. So we do care about them being really correct. If you could just like generate a dump of like 1 million lines of PTX from an LLM, it's kind of hard to verify, right? And so for one, you can actually like, if the kernel is short, you can probably still have like a human like glance over it and say, oh yeah, this makes sense, right? So at least there's like some more guarantees. But yeah, of course, everything depends on the capability of the LLMs. If we have singularity, of course, nothing matters anymore. So there's like a big space, I think, between where the LLMs are today and the singularity where nothing matters anymore.
All right. So I think just on that note, folks, I think I will sort of slow down questions because there's a lot. So we might just end up like sort of.
I'm also happy to like overflow to Discord. We can continue discussing later.
Sounds good.
Yeah, I can like hang out. Perhaps I'll try like right after this talk, maybe with like a short break. But yeah, I like happy to like expand on other thoughts later.
Sounds good. Yeah.
Yeah. Cool. All right. I think a really interesting point, though, here is that, as I said, like I can see quite a lot after having worked on Mosaic GPU. I see quite a lot of GPU and TPU convergence. If you sort of look at where the trajectory of like GPU architecture generations is, they're basically approaching a TPU, which kind of makes sense if you think about it, because TPU started out as like a matrix multiplier or matrix operation accelerator. GPU started out as, well, we just want to accelerate graphics and perhaps later compute. And then they realized that, oh yeah, now we actually mostly care about accelerating matrix multiplies, right? And there are great hardware circuits to do this, like systolic arrays, which is ultimately, why they decided to add tensor cores. But if they want to increase the efficiency and so on, TPUs have been like literally designed for this. So I'm not telling you this just to like sell you TPUs or anything. I would be also happy to talk some time about the TPU architecture. I think it's really interesting. I think the main reason why I'm showing you this slide is just to kind of try to convince you maybe that we know what we're doing. Like we are trying to design, we know where the modern GPUs are. And because we have visibility into this, I think we also have like a reasonable outlook on like where they might be going. And so I have not like fully ingested the like Blackwell spec yet, but it hasn't come like as a huge surprise. I did not have access to it before. I just like saw it, yesterday pretty much as it came out, but it was not like groundbreaking, right? It was a big architectural change ultimately compared to like Hopper and especially to Ampere, but we have kind of seen this. And so I also wanted to just kind of keep in mind that we are trying to like design those, that we think those accelerators are becoming really similar. And as we're building Pallas, we're trying to sort of take into account like the trajectory along which those accelerators are moving, right? And so, for example, the execution units, the tensor cores, the granularity at which you run them are getting ever bigger, right? TPUs are, on GPU, like now in Blackwell, you have like 2 CTA or 2 block essentially matrix multiply instructions, right? Which is quite huge, really. There's like a growing gap between matmul and vector flops. Both have asynchronous HBM to SMM transfers, essentially, that you now need to like carefully pipeline with your compute to make really good use of the hardware. And even stuff like GPUs added uniform compute just so like there are now 2 classes of registers in GPUs, and they can hold certain deduplicate certain data between CUDA lanes. TPUs also have like a dedicated scalar unit to also like discharge control flow and stuff like this. So I think there's just quite a lot of similarity. Again, interesting. I think maybe you should at some point consider expanding the group to like accelerator mode now that it's not going from CUDA to GPU.
It's like well maybe heterogeneous computing mode, I think, will be what we'll call it starting tomorrow.
Yeah. Okay. Great. That will be my lasting impact on this series. Yeah. Anyway. Okay, so now let's actually look at the realistic example of how you would implement like a sort of, let's call it, fully featured Pallas kernel. This is actually like a matmul that you could implement. The only missing feature really here is like kind of chunking up the k dimension. So kind of think about it as like this is a reasonable kernel if your like contraction dimension, the k, is small. So let's just look through what is in there, right? We have this is the full function. The matmul is like the interface to JAX. Inside it is the actual kernel function. This is actually kind of trivial. We take, again, two sort of references for the inputs, one for the output. Here you can actually better see we are using JAX NumPy functions because we just say, yeah, load both of the inputs, take a dot product, write it to the output. The kernel is actually kind of boring, right? And if you look at it, you might be kind of surprised because a few slides ago, I just showed you that, well, if you take all of the inputs, right, those are, again, trivial slices, you would end up with a kernel that has like no parallelism inside. This is not what will happen here. This is sort of the extension to Pallas call. So you still pass it sort of the matmul kernel. You still pass it sort of the type of the output so that it can pre-allocate it. You still pass it the grid, which here we just partition sort of the m and n dimensions of the matmul since they're kind of the parallel dimensions of the matmul. Now the new things are this like inspec and outspec, and they are essentially kind of, you can think about them as sort of pre-planning or sort of declaring the access pattern for both inputs and for writes to the output for every single program in this grid, sort of independently of the actual kernel. Like you can't make it data dependent, which is a restriction, but it's also really powerful. Like it actually guarantees us that we can implement pipelining, as you'll see later. So yeah, as before, the grid basically declares that, because it's 2D, we'll have like a 2D space of independent invocations of this single body. Now, everyone, for each input and for each output, you specify this block spec structure, and it has two components. The first component is just the shape, and the shape essentially describes how we are going to tile or partition those inputs and outputs into sort of disjoint segments, right? And so for the first operand to the matrix multiply, we'll essentially slice it into tiles along rows, but taking all of the columns. So you can see we slice it into chunks of BM rows, but then we take all of the columns. For the second operand, we actually take all of the rows, taking y shape 0, but then only a subset of the columns. So we divide, describe a division like this. And then for the output, we just say, yeah, we'll take actually a small slice, BM by BN, right? Now, the only thing that we're missing is actually the mapping from those program instances to those slices, and this is exactly what the second component is. So it's a little, usually for simple kernels like matmul that have simple access patterns, it's just a lambda, but for some kernels that are more advanced, it can get like much more elaborate, and then usually they're just like, bigger functions. They can still be like arbitrary, pretty much Pallas expressions inside those. They don't have to be like really simple projections like what you see here. So, and those functions essentially map the grid indices. So here the grid is 2D, so there are two inputs, to the space of the tiles of those inputs, which again, since all of the inputs are 2D, the expressions will be 2D. And so for the left-hand side, we will see that actually if we program instance 1, 2, that means that we will take slice 1, 0, which will be sort of the second slice along rows. You can see here, because we have not tiled along columns, all of the tiles actually have sort of a coordinate 0 along columns. And similarly here, all of the tiles have coordinate 0 along rows. So it's not like there's much choice that we have. But for the second operand, we do use the second grid index, for example, to select the tile, right? And for the output, we just use the full grid coordinates, which is usually the strategy, right? Usually you just like define the grid to partition the output somehow. And then, here in this case, one of the input is invariant on one of those grid dimensions, usually for a matmul. And so, as I said, this essentially describes how individual instances of this program will be accessing, reading the data and writing to the output, which what it lets us to do is, as I said, pipeline memory transfers and compute. It lets us essentially emit the async copies fully for you without you having to think about anything, right? And so the data is streaming in as you're doing the compute, and as you're doing as the output is being written out, you're still doing the compute on another instance. And so this is not a compiler optimization, right? It's not like we're looking for loops that have operations inside and reads and writes and so on. This is like guaranteed to happen just because you have specified this. And pipelining is crucial for like modern hardware. And this is why it sort of deserves this very special place in our programming model, I think. Yeah, and so actually just to give you like a more sort of concrete example, this is like a full flash attention kernel for a TPU. You can see there's like no nasty indexing really in the kernel. It's just like a bunch of reads and writes. All of the references kind of come in. Oh yeah, I should say here, as we specified those shapes, those references here now, they do not refer to the full operands. They actually only refer to the slices. So sort of a single program invocation not only tells the sort of Pallas which slices it will want, it actually can't even violate this promise because Pallas will only pass in this particular slice of the input, right? It will actually only see the strip. If you query the shape of xref, it will be this like kind of long but very short strip of the input. And so that's why there are no like slicing expressions inside. The references already come in pre-sliced. And yeah, this is an actual flash attention kernel that you could run on a TPU and it will get reasonable performance. There are certainly optimizations you can put in, but as like a starting point, this is enough, and it fits on one slide, which I think is just really neat. Yeah, most of the access patterns for those like transformer style workloads are actually relatively simple, and that's why I think this works reasonably well. What I think is also quite cool is that actually Pallas does not support all of the JAX transforms, but it does support VMAP. And so in fact, this is not a complete maybe attention kernel you would like to use. But in fact, if you take this kernel and just apply VMAP in 2 different ways to it, you just get like multi-head attention or multi-query attention just for free. So yeah, that's, I think, another kind of neat trick and feature that you get from Pallas kernels. They're actually VMAPable. They're not reverse mode differentiable automatically. They are forward mode differentiable, I think. They're surely VMAPable. And VMAP generally is also, like, again, easy to schedule because it just like creates a bunch of independent subcomputations that you can evaluate in parallel. Anyway, kind of a neat trick. Okay, now we actually move to the topic of this presentation, which is, how to use Mosaic GPU from Pallas. So we'll start with the same sort of simplest single block kernel. The only change, we import Pallas as before. Now the only change is that we additionally import from the Pallas package, we import Mosaic GPU. Conventionally, we import the backends as PL and then just like the accelerator that it's targeting. If you see PL GPU, it might refer to Triton, it might refer to Mosaic GPU. So a little bit confusing, but usually you only like use one of them. And so yeah, this is the simplest kernel. As I said before, you get those references, you read them out, you write the output. We just create the input. Now here we are actually using like a little helper for running PLGPU kernel. Pallas call would work too actually here, but as we'll get to Flash Attention 3, which will be sort of the culmination of this whole evolution now, that one will use PLGPU kernel. So I wanted to use this one because it will also support more advanced features like having a few warp groups per block, etc. Like more sort of GPU specific configuration as opposed to PL, which is supposed to be like a hardware agnostic layer. So we do not want to lock ourselves into being fully hardware agnostic, but we do want to sort of have like the biggest common denominator we can have. And this common denominator ends up in that PL namespace. So if you use PL functions, generally your kernel should be portable. As soon as you start using like backend specific extensions, it stops being portable. But those backend specific extensions should be available to you, we believe, because ultimately like portability is not that important, I think, right? Like we are writing kernels because we want the fastest code we can get. And between different hardware generations, the strategies evolve and change quite a bit. So like, why would you try to make sort of a, emulate a strategy from older hardware on the newer one? It might even run okay, but if your goal is to like reach the highest performance, then you might as well just like write a new kernel probably. It's not like a new hardware generation comes out every day, so you still have some time to like adjust to it. And so just like before, you pass in this JAX array and they become references as kernel arguments. Okay, then again, we move on. We just follow the same pattern. Now we move on to multi-block kernels. You still specify the grid of size. Here we just specified of size 2. Now one change is that PLGPU kernel actually also wants you to name your axes, so you will not be referring to them by integers. It will be names. And then you can query using lax, which is JAX lax axis index. You can query which one you are. Again, you just take a disjoint slice of row block elements and you apply this slice to references. Nothing really changes here. Yeah, grid has 2 blocks now, and again, no pointer arithmetic, just slices. Now we actually get to the sort of meat, and you can see kind of the complexity grows quite quickly as we start talking about sort of more low-level GPU features, but it will get better, I promise. So first of all, let's actually start down here. So PL run scoped is a function you can use to allocate memory. So this will invoke the scoped function, and it will give you essentially chunks of SMEM. So Mosaic GPU does not abstract memory allocations from you. You are actually responsible for allocating memory and managing it. Anytime you have a value, like an actual array you read, it will actually be probably in registers. If you read too much, you will spill, it will be slow. But at least you do have control over, in which memory space your data is, because memory space management, I think, is another crucial piece of trying to extract, performance from a hardware, right? Like Flash is fast because it manages memory spaces well. Yeah, so we will allocate essentially SMEM for both of our inputs and the single output, which is why we say we want 3 of those things. And then we also allocate a barrier, which is kind of the GPU specific way of synchronizing with async copies. which TMA in Hopper and in Blackwell as well. And then you can use a PLGPU function to copy from essentially global memory to SMEM. I should say those references here, they were actually in GMEM. So as you were doing this was sort of the classic GPU read from global memory. Now we'll change it. We'll just use async copies to sort of move the data into local memory. So those SMEM references, then we will do compute on those SMEM references, write the output to SMEM, and then ship it back to the sort of global memory using copy SMEM to GMEM, right? You can see still it's not that complicated, right? As you say copy, you can use this at operator to pre-slice a reference without actually loading the elements. So you sort of say, oh yeah, just only look at the slice of the global memory, but copy this slice into the entirety of LSMEM, which will be a lot smaller at this point, and use this barrier for synchronization. Do the same for the right-hand side, and then wait for the transfers to complete, right? So you can see, it's more code, but it's not unreasonable, right? Like it still automates a lot of the boilerplate, like creating the descriptor on the host, shipping it onto the device, managing it, right? Like actually sort of reduplicating, reusing the descriptors as much as possible. Essentially, TMA is not that user-friendly as a feature, I think, but I think we've managed to like find a reasonable abstraction for it, right? And so this is what I'm saying. This really does not take away any control from you, but it does enable you to sort of use those low-level features without having to think about all of this like nonsense and noise that is automatable. Right, and to simplify this, actually, you can even get something better. You can use emit pipeline, which is a helper that, again, this is the compute. We just abstracted it into like a little function. Now we'll say we'll actually do our compute in multiple steps. This was kind of a dumb kernel to have, right? Because we scheduled async copies and then immediately waited on them. And then we did our compute, and then we scheduled our copy back to GMEM, and then we waited on it immediately. So again, we haven't really done any async copies here. So actually to do them, this would be a lot more involved. You would have to like write a loop and like pipeline it. This is annoying, but it's also automatable again. And so there are helpers for stuff like pipeline. You can just emit pipeline, and just like you saw before, you can pre-declare your access pattern using those block specs. And so here, before we were just like essentially slicing only half of the rows in our 2 blocks. Now we're also slicing each block handles half the rows, but in a single step it will also only compute on like a quarter of the columns, and we will process our data in 4 steps. But between those 4 steps, we will overlap like loading the data onto the fast local memory SMEM and sort of storing the results back. But all of this happens just through emit pipeline. You just say, okay, I will want to run compute this many times. Again, it can be like a nested loop, it can be an ND tuple, and this is the access pattern for like which slices of the inputs I will want to read at each step and which slice of the output I will want to write at every particular step. And then you just pass in the GMEM references, and your compute kernel gets the SMEM references. All of the transfers are managed for you automatically. There's like no need to actually spell them out, which I think is, it's pretty simple. Okay, then there are also more features. Like TMA is a pretty powerful abstraction. You can do kind of quite cool things with it. Like you can apply swizzle, which is generally just like a permutation of data, which helps you avoid bank conflicts for performance reasons. You can also reorganize sort of the order in which the data is stored in memory, which is useful for stuff like actually targeting tensor cores, because these days tensor cores do read the operands from memory most of the time. This is like the best way to use them. And so in particular here, we use a tiling transform. Recall that our input is actually 128 by 128, right? And so that would be the full matrix. If you were to store it out in memory, conventionally, you would use like a row major layout. So you would essentially traverse the full first row and store the elements linearly. Then you would move on to the second row and sort of keep scanning, then to the third row and keep scanning, and so on, right? Once we tile this, essentially what this means is that we change the order in which we want our elements to appear in memory by sort of scanning here up to, we take slices of 64 by 32. So still going row major, we still go up until we reach the 32nd column, and then we sort of wrap back to the row, right? And so we sort of do row major within this 64 by 32 tile, and then once we run out of this tile, we move on to the next one, and again, we do row major here. So it's essentially first row major within the tiles, and then row major across the tiles. Kind of a weird transform to do, but it's actually really useful for tensor cores. And actually, by playing stride tricks, you can get the TMA engines to do this transform for you on the fly for free. Like they will literally like reshuffle the data as they're copying it into SMEM, which is pretty powerful. That's like another cool technique, I think, that you can get out of Mosaic GPU. Then finally, we get to WGMMA. Yeah, something to note, the transforms you specify on the block spec, only now those transforms are GPU specific, so we use PO GPU block spec, right? Again, platform specific API. And then finally, we do have WGMMA. And this again gets slightly more complicated, but if you look about it, there's not that many new concepts. So first of all, you still emit the pipeline. If you look at those block specs, they're essentially kind of the same block specs we had before for the example matmul kernel. The only exception is that you specify those transforms, which will sort of rejiggle the memory as it gets shipped into local memory from the global memory. And then this is the actual compute part. And so you can see we actually allocate like a little accumulator. Tensor cores usually not only multiply to matrices, but they also accumulate into usually registers. Now it changes a little bit. So we do model this as a reference. So again, this is run scoped. It's just the allocation thing. Then inside here, you just run WGMMA. And WGMMA is the tensor core instructions from Hopper. It will read 2 operands from shared memory and write it there. And then as you dereference it, you can accumulate it here. This is not the best way to run a WGMMA, but this is sort of the simplest thing that fits on the slide. Yeah. Cool. And I just want to, this is completely different code, but actually this is one feature that we have not exposed to Pallas yet, but I do want you to see it because again, I think this is another example for how we're trying to automate annoying things. This is a sort of, again, dumb minimalistic WGMMA example in pure Mosaic GPU, not in Pallas. So this is sort of using more, like you can see this arithmal I, GPU block ID, blah, blah, blah. Those are all MLAR operations, and this is how you would program direct Mosaic GPU directly. Now, if this is like a minimal WGMMA example, to add block clusters and TMA multicast, which is a really powerful sort of concept, but also kind of really complicated, I think, to use correctly, right? The idea there is that the GPU is able to take a slice of global memory and essentially actually write it into the shared memory of 2 distinct blocks on like 2 different ascents, right? Which if you think about it is kind of mind-blowing because blocks were always supposed to be this like unit of parallel work that do not really talk to each other. But now like one block can say, oh yeah, I want to copy this piece of data and by the way, write it also into the memory of the other block, right? And so it's kind of like a weird thing to program. Actually, if you want to do this in Mosaic, you can make it remarkably simple as it turns out. You can just configure, just like before you had like a 3D grid, you just configure a cluster dimension because the 2 blocks have to be within the same so-called cluster of blocks. And then if you just want to use this on the async copy, or in Pallas, this would be copy gmem to smem in this case, you just say, oh yeah, this copy, make it collective along GPU dimension X. Essentially, what this means is that Mosaic GPU will expect you to run exactly this same copy on all of the blocks that share the same sort of X coordinate in the cluster, and it will sort of rewrite the program so that every block like only does a part of this transfer, but it will use this feature where it's like written to multiple places in the end, and so in the end, everyone gets all the data, right? I think it's pretty cool, and it's just like a tiny change to your program. Again, I think this is boilerplate, just like juggling those instructions, but deciding whether you want to use this, it's actually quite non-trivial. Like using clusters has like an implication on occupancy, which, you can underutilize your GPU because you can't use all the other, it's really involved. So making the decision to use this or not is what is complicated, but sort of implementing it is also complicated, but kind of not interesting. Like you would always implement it in almost the same way. And so again, this is kind of what we're trying to automate. Yeah, and through this short run, we've ended up using most of the features that were introduced in Hopper. We use TMA, which are the async copies. We use WGMMA, which are those warp group wide tensor cores. And in this last snippet, you also saw block clusters and TMA multicast. We're working on exposing those to Pallas. So hopefully next time I give this talk, I'll be able to use fully Pallas Mosaic GPU examples. Yeah, and what you can do with it, well, can it actually do something useful? The answer is yes. I think the nicest kernel, the coolest kernel maybe, that we have is actually Flash Attention 3, which actually coincidentally we have somewhat developed sort of concurrently with the original one. Anyway, the performance numbers are pretty good. Like we are actually able to get like above of 70 something percent tensor core utilization on Hopper. This is the exact parameter that I benchmarked it at, which I think is pretty cool. And the kernel itself is actually not that long. This is like a sort of more complicated kernel. If you like take it's fully open source. You can find it at this link. And if you look at the sort of difference between where it starts and ends, it's actually 150 lines of Python. So it's not that complicated, right? As I said, it's very information dense. Usually most of the lines are very load bearing, but hopefully it should not include that much boilerplate. Actually, this is false. This one includes a bit of boilerplate that deals with word specialization. We just yesterday checked in a new helper, which is like a generalization of emit pipeline that emits a word specialized pipeline. That kernel is under 100 lines, which I'm really proud of. And it's not like, it specializes something particular to attention or anything. It just like gives you access to another easy configurable strategy for pipelining. And yeah, it shortens this kernel quite significantly. Okay, here I was planning to take a look at the code, but I kind of didn't plan for, I guess, the language war. So I guess you do have the link. Maybe this is the part of the presentation I'll skip just so that we actually do have maybe some more time for the questions at the end. One thing I do want to show you, though, is another cool feature that we have is actually work group level profiling. I'm very proud of this one. And so we'll quickly break out of the presentation for now. Yeah, this is.
Oh, yeah, actually, Adam, we don't have to do Q&A considering you're going to be hanging out on the server. So please cover all the content you'd like to.
I mean, I think it's not that important. I can kind of go over the kernel, but yeah, given the I don't know. I mean, we're already at an hour. I still have like a few things I wanted to say, and I think this will actually be sort of a nicer demo maybe than the code walkthrough. I'm also happy to like answer any questions. Maybe one thing that I'll show you is how the word specialization looked like before and how it will look with the new helpers. So hopefully maybe let me make this a little bit bigger. You should hopefully still be able to see my screen. Anyway, so this is where the kernel begins. And as you can see, essentially before we just computed the warp group index, which was again like one of the okay, I should actually first show you how you allocate multiple warp groups. So here, as you use PL/GPU kernel, the only thing we have changed is that we said num threads 3. And so what this means is that each one of those programs along this grid will actually have 3 threads inside. And so you can see we specified the 4th axis name, which here I have called warp groups because, well, each Mosaic GPU thread is a warp group. And so then we can query here inside the kernel which warp group we are, which happens here. And then essentially the whole kernel is just wrapped in like 2 conditionals. So one begins here. And so you can see we select the first 2 warp groups and they will be doing the compute. And this is kind of the bulk of the kernel. It ends kind of here. And then the last one will only be doing like copy gmem to smem or pretty much copy gmem to smem. That's all it does, right? And then they synchronize through barriers. Like you have PL/GPU barrier wait, you have PL/GPU barrier arrive. And this is kind of, we also allocated those PL/GPU barriers, which is how they can talk to each other, right? But this is kind of annoying and error prone, right? Because this compute thread, it only waits for the memory to arrive. So you kind of want to say, oh yeah, I wanted to read some memory here, but then you have to scroll here to like a completely different thread. And only here you say, oh yeah, actually load this slice into this part of memory, right? It's kind of error prone, like the load happens far from where you're actually using the memory. It's kind of annoying. So essentially what I just wanted to show you is, now you can just say, where is it? Yeah, here. Emit pipeline warp specialized. And again, you actually specify the axis pattern here using those block specs again. So you say, oh yeah, we'll be taking slices along our K tensor and along our V tensor. the sort of code for the warp group that does the transfers is generated automatically, essentially based on those. And then the compute thread function here is just just gets the operands. Where is this? No, sorry, this is here. KV pipeline. You just get K SMEM and V SMEM, and you just know they're there essentially, right? You don't have to even wait for them. The only thing you have to do is you have to arrive to sort of indicate that you're done reading them, so that they can be overwritten with like the next thing you'll want to access. But so the whole compute part essentially shrunk from here to here, right? This is it. The rest is just setting up. This is kind of the prologue epilogue, what happens before and after this pipeline. And in here you can see we just do like QK, then we do softmax, and then we do the result of softmax with V, and that's kind of it, right? And so that's essentially what we're trying to achieve. Warp specialization gets like seems like a mystical technique, and in fact there's like a lot of magical numbers often flying around, like the whole allocate deallocate registers. But in fact, again, it's like a very largely automatable strategy you can use to implement pipelining in your kernels. And so we want to give you helpers to do this nicely without having to fully understand it. Well, okay, actually, without fully understand is the wrong thing to say. I do think it's worth understanding what it does to use it effectively, but you should not have to like implement the same strategy with like conditionals and like things that happen far away from each other. It should be easy to change this kernel to, for example, not use warp specialization anymore, or to go from a non-warp specialized kernel to a warp specialized one. It should not require like a ton of code changes, and this is kind of what we're trying to achieve here. Okay, so this is the code. I think those are the biggest takeaways that I want you to have from this. If you have more questions, again, happy to follow up on Discord. One other cool thing I wanted to show you about is there is actually a profiler. I slightly had to modify this kernel, but JAX is a feature called namescope. It's named scope. It's just a context manager that is used to essentially annotate anytime you profile a computation. Now we've added support for namescope inside Pallas as well. And so you can also generate very fine-grained profiles of what's happening on your GPU. And so I have especially applied it to this kernel here. What it generates is just a JSON file. You essentially have to specify a directory where it will be dumped. It generates a JSON file, and you can open up Chrome tracing, or you can open up Perfetto, depending on what you like. You can drop the file there. I have to wait a little to let it import. And there you go. This is what happened in our kernel. Now, how to interpret this? Each process here, you can see there will be multiple processes. Actually, the way it's implemented is every process is a single SM on a GPU. And so in particular here, you can see that sort of we only, this SM was first working on some, each process is an SM. Each line here, or each thread in this simulation is actually a single warp group. And so you can see that, because we have a 3 warp group kernel, those regions for slight arithmetic issues, ideally they would be perfectly non-overlapping, because we can only fit one block on one SM at a time. And so you can see that generally there was only one block running on this particular SM at any given point in time. But if we switch to process 2, there will be other SMs, there will be other blocks, each block with 3 warp groups running in there. And then you can zoom in, and in each of those lines you can see at a given point in time, what was this block working on, right? And so in attention, again, you have 3 things that have to happen. So, each third thread here, or warp group here, will be the memory thread. So you can see it has different events than the other 2, which are the 2 sort of compute warp groups, which both compute attention, right? So their sort of pattern of events will look very similar. And so you can see the sort of memory thread is mostly waiting for the other threads to sort of indicate that they have consumed the data, so that it can, schedule the transfers. Here is, how long it took to schedule the transfer, and then, it waits for another signal, right? So it doesn't do anything interesting, but you can roughly see how long it takes. Now, looking at the other 2 threads, you can see there's a repeating pattern of you do QK, then you do softmax, and then you do, the result of the softmax, which I call P, multiply by V. Now, one interesting aspect of flash attention 3 is that you use this special barrier to make it so that exactly one of those two warp groups is computing softmax, while the other one is computing the matmols, so the PV and the QK, right? So essentially, you want to sort of make softmax like a critical section. And why do you do this? Well, softmax uses the ALU, which is like one set of hardware circuits, and the matmols or use the tensor core, which is the other hardware circuit. So by having sort of two threads of control, each one talking to a completely different set of hardware circuits, you can sort of try to utilize both as well as possible, right? Ideally, what you really care about is using tensor cores at 100%. But you just want to make sure that the ALU is not like starved. It's not like both are trying to run a matmul at the same time and fighting for the tensor core, and then they both move on to do the softmax, and now they're both fighting for the ALU. No, you kind of explicitly sort of stagger them so that both hardware units are utilized at the same time, right? Now, how does this appear here? This is a trace that I've run with head dim of 64, which is relatively small. Essentially, one interesting thing is that as you scale up head dim, your attention becomes more intense on the matmols, but the softmax cost stays the same. And so you can actually see this really well here. You can see I have annotated those softmax barriers here. So this is the point where the two warp groups kind of exchange which phase they're running. Like, am I running matmols? Am I running softmax? You can see that as part of QK, we are waiting for the other warp group to tell us it's okay for you to run softmax now. And you can see it takes a while, right? While here at the end of the softmax, it actually almost never takes any time or a very short time just to sort of indicate the other warp group that, okay, I'm done with softmax, right? So essentially you can see that the matmul phase seems shorter than the softmax phase. They appear the same length just because of the softmax barrier, right? But actually your matmul was probably done like somewhere around here. And then your warp group was just like idling. There was no more job to give to the tensor core. The tensor core is really fast on those GPUs. But the other one was still not done with softmax, right? And you can see as soon as sort of they both enter the barrier, they exchange, and this one starts running softmax, and this one starts running matmols. Anyway, now if we use head dim 256, again, we have to wait for it to load a little bit. Now, if we zoom in here, you can see the situation is actually reversed, which is great, right? This would explain why on one of those previous slides, you saw the utilization of head dim 64 be much lower than the tensor core utilization of the head dim 256, right? Because here you can actually see, well, the matmos got so expensive that the softmax barrier that happens here is actually really fast, right? Every time you are in the QK, you are actually unblocking the other group that is already done pretty much running softmax. You're allowing it to now start running matmols, right? So now you can see the matmols became more expensive. Now it's softmax that is padded with this extra sort of purple chunk here, which is actually waiting by the warp group to begin to move on to the next batch of matmols. And this is why, you can see this really high utilization, right? Because you can see the blue is pretty much happening all the time. Either one warp group is occupying the tensor cores, or the other one is occupying the tensor cores. It like happens all the time. You're not spending pretty much any time waiting for, being allowed to stop using them. You always have someone who's like ready to begin using them. And that's what drives the big utilization. Anyway, I think this profile is really powerful because you can see those things. You can see, whether you have aligned the synchronization well. You can actually see this pattern of them like exchanging what they're doing in different points in time. You can see the relative costs of like softmax and matmols. I think this is really powerful. This was really helpful as I was developing this kernel and optimizing it, just to like see where the bottlenecks are, right? Here, I have not actually annotated any of the like memory-related things besides what the like memory warp group is doing. But you can also see, for example, that your kernel is memory bound, right? Because you would see like big waits as you're waiting for memory to come in, and then just like little snippets of compute, and then a big wait again, and then big snippets of compute. So you wouldn't actually have to like do napkin math to figure out like the roofline model or anything. You can like literally see pretty much what the kernel was doing at any given point in time. Yeah. All right. Let's get back to the presentation. Okay, so this is the end, pretty much. I just wanted to, again, touch upon a few things with our design philosophy, just to sort of wrap up. Yeah, so as I said, peak performance is a goal. As you saw, like, we're not really going after having like a unified language for all of the hardware. We do want to like expose every single sort of quirk of the hardware. We do want to make the sort of common denominator as big as possible, but this is really not the goal. Again, we do not believe that kernel languages are productivity tools first and foremost. You should start with your program like written in plain PyTorch or plain JAX. You only reach for a kernel language if you're like unhappy with the performance they deliver. And so it's not that important for it to be like the easiest to use, but it is really important for it to be able to deliver the performance, right? Because you've reached for it because of performance in the first place. Right, but of course, tasteful API design remains important. We're not arguing about this. We do want people to be productive. Yeah, portability is welcome, but not, but it's kind of secondary. Again, we do want to automate as we can stuff like, writing pipelines, pipeline loops, which overlap compute and memory. It's kind of, mostly mechanical. But there's not that much like smarts you can put in there. But there are things where you can put in smarts, right? Stuff like tile size selection, or how do you pipeline over various hardware resources? And we have lots of hardware resources we can try to overlap the use of, right? We have communication between the devices. We have transfer between different local memories, right? We have vector compute, the ALU that I showed you before that does the softmax, and we have matrix compute, the tensor cores, right? I have actually not even touched upon communication here. Mosaic GPU does not support communication yet, but in fact, if you were to write TPU kernels with Pallas, you would also be able to like schedule transfers between different devices, right? Over essentially ICI, which is like the TPU's NVLink. And you essentially, the goal as you're writing a kernel is to use all of those resources as well as possible at the same time, right? And so there's like a lot of juggling, and it's really hard for a compiler to do a good job with like managing all of this happening at the same time. Yeah, and for Mosaic GPU, again, state-of-the-art performance, that's like first and foremost. I do also want to keep it a research platform. Ultimately, the way Mosaic GPU started was I just wanted to learn about Hopper. And I kind of, tried building like a playground for myself. And then I just figured, hey, this would actually, I implemented some kernels, they seemed useful. And so we've kind of developed it into a more fully featured thing. I do try to keep it as a relatively lightweight thing. I do care about it changing. Again, Blackwell is very different from Hopper yet again. And so we will want to apply changes to it. Keeping it lightweight makes it easy for us to do those things, and also hopefully makes it easy to read it. You can find out how it looks like. You can use it. You can hopefully even contribute to it. So yeah, well tested. We do care about it being correct. We're not aiming to replace Triton. I think our priorities are like slightly different. Triton definitely goes more for like convenience, and so perhaps I think it will for pretty much forever be maybe easier to use than Mosaic GPU. But it's okay, right? At different points in time, you might want to use different tools. We're not really trying to do a replacement. We have, I think, a pretty good relationship with the Triton community, and we're just trying to learn both ways. Definitely, Mosaic GPU takes a lot of inspiration from Triton, and if you look at like the history of Triton PRs, there were also some features that were inspired by certain developments from Mosaic GPU. I want to keep it this way. I don't really want to make it a zero-sum game. Yeah, portability, not a goal. Convenience, not the first goal. And yeah, this is essentially the third backend to Pallas. Okay, how do you get it? Yeah, it just comes by default with JAX GPU. So anytime you install JAX, you should be able to install it. I would also recommend oftentimes using nightly releases, since then you just get like the latest feature. We are still actively developing it, so many of the features that were added recently may not be available in the last release. Then you can just do this. And yeah, can you use it with PyTorch? Mosaic GPU, yes. You just use a different function with pretty much the same API to wrap a kernel, and then instead of giving you a function that takes JAX arrays and returns JAX arrays, it just gives you a function that takes torch tensors and returns torch tensors, and that's it. Pallas, Mosaic GPU, we don't have torch bindings for this yet, but ultimately it should be feasible to build. We do want to build it. So yeah, not right now, but ultimately why not? And if you're interested, everything I talked about is open source. Issues are welcome on the Jack's repository that talk about this PRs. You can also just send it to Jack's GitHub. Although if you want to send PRs, maybe first, do actually reach out. I am in the GPU mode Discord, so you can find me there. Or you can also just like write to my email, or the email I have on my GitHub or something. Just to give you some example projects that I think would be cool to actually do. They might be a little bit more involved, but we would not do it if it was easy. For example, we have this Flash Attention 3 implementation, but we do not actually have a backward pass for it implemented yet. I think it would be really neat if we would have like a more complete package where we can, essentially provide like a single operator for this attention for Hopper. And now that Blackwell documentation is public, I am hoping that we'll be able to program Blackwell relatively quickly. Hopefully we'll be able to apply it there as well. Another thing, better FP8 support. I have not really played much with FP8 or lower formats. It would be nice to support them. This should be hopefully more incremental. Another neat feature to develop. Another one, I think it would be actually really cool to try out, implementing, splash attention from Jax or flex attention from PyTorch, but actually give it sort of Flash Attention 3 performance. You could turn Mosaic GPU as like a template for this configurable attention and just like generate really good attention kernels from this. And then finally, something I want to explore are mixed precision matmos. I think those are actually kind of cool because, again, sort of converting between different D types involves a little bit of ALU, while doing the matmos well involves the tensor core. And so, again, you have to like carefully manage what's happening when, just to make sure like tensor core is not, starved by waiting on the ALU. So takeaways, I think that Hopper kernels and Blackwell kernels, hopefully soon too, I think they can be reasonably concise, even though they, sometimes you will be reaching for somewhat low-level tactics. You should still be able to prototype them in Python reasonably well. The next steps, we are working on essentially making it slightly higher level. So you might have seen there are some like layout casts. Essentially, you do have to like manage the way your arrays are like partitioned over registers. It's not fully automatic. It's not as nice as in Triton, for example. So we do want to automate this part a little bit more because we think it is feasible. And also annotating those TMA transforms. You saw there are some like magical numbers in there. That would be good to automate. That's something we're working on. Blackwell support, we're very much working on this. And finally, I think it would be really neat if we could also like, use the same techniques we use to write TPU collectives and essentially start writing NVLink collectives where we like overlap compute with NVLink transfers, not just compute with like transfers between the local memory regions. This is something we have planned, but probably a longer timeline. And we'd love to collaborate, but do keep in mind that this is like, we give no stability guarantees for this at this point. All of those things are still being actively developed. And so, we'd love to have you follow along. But if you want to depend on this in some capacity, that would actually make us happy. But please do let us know because, otherwise we might break you. Cool. That's all I have for today. I think we're a little bit over time, but maybe we can still take a few questions and then, the overflow I can do on Discord. So thanks for coming.
Thank you, Adam. I guess like if people have any questions, let's sort of speed run through them to be respectful of Adam's time. I saw like there was like a bunch of questions by Daniel. Like one was, can you expose Hopper's setmax RNG PTX ISA instructions in this programming model?
Sorry, this is the like register allocation deallocation. Is that the setmax and reg? Is that the one?
Yeah, I think so.
Yeah, this is exposed. If we look through here, there you go. There's PL GPU setmax registers, so it is directly exposed there. I honestly think this instruction is kind of insane. Like the fact that it exists in PTX is a little bit insane, the way it's encoded. But it is actually important. So we just like expose it this way. Although if you use this yeah, again, this like 232 is like a weird magical number that you can see floating around. But actually, if you understand how it's computed, it's not that complicated. So if you use this like helper for a mid pipeline more specialized, it actually does it for you automatically. The only magical number you specify are how many registers you want to sort of donate to the memory warp group. And then all of the other warp groups become compute warp groups. They will like partition the remaining registers evenly among them, again, using those instructions. So yeah, it's exposed, but again, we're hoping that you will not have to use it.
Another question by Daniel. What is the mechanism by which you record the time of each region? People usually use NVTX ranges or CUDA events with timing, but those are both host level APIs and can't be used within a kernel.
Yeah, exactly. So this is like a little homegrown profiler implementation. That's also very unsafe. Basically, the way it works is you have to also, as a parameter to the profiler, you specify like how big of a memory region in SMEM you want to allocate for the profiler. And then essentially as the kernel runs, you probably want to like make it a reasonably short run. So like don't run it on like a, I don't know, 128K sequence lengths or something. Yeah, and then each warp group is just like storing events into SMEM. Each one gets like a disjoint region, so there's like no synchronization, and it's unsafe because there's also no bounce checking, because I don't want like this to have any overheads really. It still has slight, but I want to make them as minimal as possible. And then once the kernel is done, yeah, there's just like an epilogue phase where like a single thread just like copies this like log of what happened into GMEM, and then there's like a little Python snippet that interprets this. In fact, if you just go to, yeah, so there will be Mosaic GPU profiler Pi. Yeah, this is pretty much the whole implementation. It's like 400 lines. You can just read through it, hopefully. It should answer it. But yeah, it just dumps events into SMEM, then to GMEM, and then there's like a little Python script that interprets them once the computation is done. And yeah, I just use like PTX instruction to like extract performance counters or something. There's like this clock register or something that's special.
Eric Schultheis is asking, like earlier you made a comment around how like enterprise data, like how around data center GPUs and TPUs are converging. Would you sort of, are you making were you making the more specific claim of like the data center ones are converging, or just generally that like GPUs are converging as well? So like he's wondering if your point applies to gaming GPUs as well.
Yeah, this is an interesting question, right? I mean, NVIDIA very clearly is separating gaming GPUs more from the data center GPUs, right? Like usually it was like a single hardware generation, and then they just like specialized, like maybe capped the hardware sometimes and just like made it into like a gaming GPU. These days, like, you know, there's no gaming Hopper, right? Or I don't even know if like there will be a gaming Blackwell or something. So yeah, I'm primarily focusing on the data center products. The gaming ones, you know, I think if they will want to accelerate Matmos more, and there are, you know, legit reasons why you want Matmos in gaming, like DLSS, I think is really awesome. Yeah, maybe, you know, they will also like steer more towards this direction. But, you know, for gaming, I think this like vector side is still much more important than the tensor side. But yeah, this would be my guess, but I don't feel extremely confident in that answer.
All right, and then I think the last question we have is from Albert Aye, which is, can you use Pallas to give compiler hints to XLA instead of having to write an entire kernel? How do XLA and actually Jake Canal is responding that the GTX for 5090 is Blackwell. So
nice. Okay,
yeah.
I don't know.
Yeah.
Yeah, but I'm curious if it will have the same tensor cores, the like big ones, because yeah, it was really interesting to me that Hopper, there was no gaming product that used it. I am curious. Yeah, I haven't investigated, so I do not have much time to look into Blackwell yet. So maybe I should stop that.
Yeah, I think there's a lot of speculation in chat at this point, so maybe we'll go on to the last question. So basically, can you use Pallas to give a compiler hints to XLA instead of having to write an entire kernel? And so how do XLA and Pallas interoperate?
Yeah, that is a very good question. So no, we are planning. So definitely in JAX, we've been also moving there has been a trend to develop sort of more control over the compiler scheduling and fusions and layouts, inference, and stuff like this. But those generally fall into jacks. As soon as you start using Pallas, that is kind of a hard boundary where you say, no, at this point I stop using XLA. I will be using a different backend. I think interestingly, Pallas actually does have you can pass in like interpret equals true to it, and then it will actually generate XLA computations from it, but it's mostly meant for like validation and not for actually generating high performance implementations. So no, as soon as you transition to Pallas, you are generally in a different code gen. But having said this, we are trying to sort of make this not a complete black box from the point of view of the compiler. So for example, on TPU, the compiler actually, if you allow it, there's like a flag you can specify on like a parameter on the kernel as you instantiate it. You can enable the compiler to actually fuse into your kernel. Like if the input computation that produced one of the inputs of your kernel can be reasonably fused into the kernel, the compiler can actually try to do it for you. Or stuff like cost analysis, you can actually provide like cost estimates of how long your kernel takes, which can like improve the scheduling the compiler does around your kernel. So we do not want Pallas kernels to be essentially full black boxes, but it's not possible to say just like override one little aspect of like XLA compilation. As soon as you enter into Pallas kernels, you're kind of in a world where you're just writing a separate program. But we do want to make it understandable to the outside world as the compiler is generating more code around it. Yeah.
All right, and with that, thank you so much, Adam. Folks, if you'd like to see Adam come by to give us another talk, like please let us know in chat. Otherwise, Adam, this was fantastic. Thank you. And if like more folks like that, like if you know of like more systems folks that work with you who would like be interested in giving a talk, we'd love to have them. So thank you, and we'll see everyone soon.
This was super fun. Great questions too. So yeah, thanks a lot.
Thank you.